Good afternoon, everyone. This is Cassandra from NOAA Library. Welcome to Library Seminars, the library's online platform to highlight research and ideas relevant to NOAA. Today's presentation is part of NOAA Fisheries Ecosystem-Based Fisheries Management Series. The series coordinator, Corinne Burns from NOAA Fisheries Office of Science and Technology, will introduce our speaker here in just a minute. One second. Corinne's computer crashed right as we went live, everyone. So give us 1 minute as Corinne reboots. Okay, so it might take Corinne a second to get back with us, so I will go ahead and do the introduction for today's presentation, which won't be as nice as how Corinne would have done it, but we'll be able to keep you all from having to wait even longer. Today's speaker is Dr. Tom ID, is a fisheries ecologist specializing in the identification and quantification of ecological impacts of human-induced changes in marine systems. He has nearly 3 decades of research experience in the Chesapeake Bay system. Dr. ID's work focuses on the development of ecosystem models that estimate the future status of our natural resources under different management choices and the assessment of the health and status of the blue crab population in the Chesapeake. Thank you for joining us today, and I will turn it over to you.
Thank you, Cassandra. And just thanks everybody for coming today. I'm going to spend a bit of time reviewing the results of a recent work quantifying the ecological and economic impacts of foundational habitat changes in the NOAA habitat focus area of the Middle Peninsula of Virginia, and that's part of the Chesapeake Bay. My co-authors here are listed, and I especially everybody. This is a nice team approach, and everybody contributed quite a bit to this project. But I did especially want to call out um, my PhD candidate in my lab, Amanda Bevins, who made most of the images that you'll see today. So we used a combination of ecological models and an economic approach to estimate economic impacts of this habitat changes that are taking place here. And 2 habitats are changing simultaneously. So oysters were restored here, but we also know that another very important habitat, eelgrass, has been decreasing over the last 100 years. And that's due to both poor water quality and temperatures that are increasingly too warm for the species. Um, and We quantified these regional economic impacts of the changes to both understand what the impact of the oyster restoration has been in 2 tributaries here, as well as what the future economic impacts should be expected in this area. And where are we talking about? Sorry, I'm going to use some control. So this is the area of the NOAA Middle Peninsula Habitat Focus Area and our area of study. And there's 2 tributaries here where we developed individual ecosystem models for both the Piankatank River and the York River. And these are the rivers where oysters were restored. We changed the um, the main tool we used was EcoPath with EcoSim, and that's a trophic model. And our goal was to change these foundational habitats both singly and in combination, so we could get at the compounded effects or start to get at cumulative effects and understand the changes that take place here. The model is focused on food web and predator-prey interactions, and it takes a mass balance approach at its core. It assumes that all those groups that are present here have enough food, and that as we go forward in time, that assumption continues to be true. And that's not an unreasonable expectation based on historical presence of these species. And the models were built with 49 different groups, and they have the same structure in both models. These rivers are fairly close to one another, and they include the population dynamics of all those groups, biomass and density and mortality rates, consumption rates, and the diets, of course. We account for environmental variables, we account for fisheries harvest that are taking place here, and those two habitats I've been talking about, the oyster reef that's been restored and submerged aquatic vegetation that's changing, are two of the living groups of those 49 groups. As I said, we're simulating them both singly and in combination. And once we've got estimates of the populations in the future, the forecast of those populations, the forecast of the harvests that take place, the last step is translating those harvests into regional economic impacts, different metrics that we can produce with the in-plan model. I want to spend a few minutes talking about the scenarios that we ran. So the scenarios themselves are quite important to understand for the rest of the presentation. And they were fit to time series of actual data, indices of abundance from the state of Virginia, and phytoplankton change data that we've got from the Chesapeake Bay program on chlorophyll A also constrain the model fits. Inputs of environmental responses of temperature, salinity, and dissolved oxygen were used to tune the growth of each individual of each individual group in the model of those different species that are included. We're looking to constrain their growth, what's optimal, what's suboptimal, and that was all accounted for. And so the specific scenarios included oyster-specific scenarios, and the young reef is our current status. So this was a recently restored oyster reef. And along with that, we thought it was important to understand, well, what was the system like before that restoration took place? So that's another scenario. And then also, what is the system going to be like if we allow that restoration to mature? And the assumption here is that we would see a 4.7% increase annually. And that's based on observations from another restoration that took place in Maryland. And it's important to realize that that 4.7% annual increase is probably an underestimate because oysters just don't grow as fast in Maryland as they do in Virginia, where these models are developed. Another thing about these scenarios, it's important to recognize that it's not just oysters that were simulated. We also realize that the oysters, as they grow, provide more surface area for other filter feeders to grow. So we're also simulating tunicates, hooked mussels, barnacles, and sea anemones. And we assume because they're tightly linked to the space that they need to survive, that they grow on the oyster reef, we also assume that they are increasing at a 4.7% annual rate. Seagrass scenarios, we've got our current eelgrass um, uh, abundance is simulated in the central scenario, but we also realize that that population is continuing to decline. So we wanted to understand what happens to the ecology when we've got less eelgrass. And, and similarly, um, if we were able to restore that eelgrass population, there are efforts to look at subspecies or different lines that can tolerate warmer waters. And there's also a possibility of other seagrasses taking the place of eelgrass. we wanted to understand what the ecosystem would be in that case as well. And we simulated, in this case, um, what the population would be at a recently observed maximum seagrass coverage. Similar to the oysters, we're also simulating small crustaceans that are associated with eelgrass, very closely associated with them, as well as some clam species. It's also something to note that although the eelgrass is the main focus, we also simulated widgeon grass. This is a seagrass that fills in when eelgrass is lost. So that widgeon grass is also a part of these simulations, but widgeon grass is not deeply rooted. It doesn't have the same ecological value as eelgrass, and we accommodated all those aspects in the simulations. Then we also simulated a variety of combined scenarios, a decline of both habitats. Uh, what would it look like if both habitats were restored? And then what we viewed as a more likely future scenario are oyster restoration in combination with an eelgrass decline. So I want to spend a few minutes just talking about outputs. And with these approaches like EcoPath with EcoSim, ecological models have a huge variety of possible outputs. And these output metrics are important to really think about um, for a variety of reasons. The most common output that you see is biomass. That's the raw data that, or the raw output that comes from these models. It could be grouped by trophic yield. It could be individual groups themselves by ecological niche, or by the system-wide biomass as a metric in itself. These are all possible metrics we can look at. Similarly, projected landings could be an interesting output to look at. Um, Other ecosystem services. So these are other things that are important to people, things that would affect populations, things that affect our people, could uh, be metrics of output, as are a huge variety of ecosystem indicators. Ecosystem indicators generally look at the status and function of the system. It might commonly be focused on trophic condition, and some of these types of indicators might be expressions of diversity. There's more than one way of looking at diversity in the system. It might be the metabolism of the system itself, the energy balance of the system, um, before and after a different scenario is visualized. It could be the coupling and the relative tight or loose coupling between the benthos and the pelagic species, or consumer relationship to producers, or that ratio. Many, many different ecosystem indicators have been tried, and I'm going to show you both some examples of ecosystem indicators. That's what I'm going to start with, and I'm going to end with focusing on a particular group that's probably of most importance in the Chesapeake Bay system, in terms of um, finances, and it's the most lucrative seafood species, the blue crab. So we'll spend quite a bit of time looking at that. The overall, though, here thing to think about if you're working on this type of approach is it's important to understand what the stakeholders need to see. So it's it's very worthwhile taking the time to communicate to the people you think you're producing these models for, and what information is needed, what trade-offs do they need to be informed about. And we'll see a little bit more about this later on in the presentation. So as I said, I'm going to start with some look at some of these ecosystem indicators. And just in general, before we get into this, The y-axis is going to change in all of these figures, and the actual numbers is not as important as looking at the trends, the dispersion of the different scenario results, um, and how they relate to one another. Here's our projected time frame over time is on the x-axis, and our scenarios are abbreviated here and color coded. So just to orient you to the results here, all of these are going to look fairly similar. These are abbreviations for the different scenarios, just shorthand. Oysters are increasing, eelgrass are increasing in this first example on the right in the key. Eelgrass is increasing by itself, and oysters, we didn't do anything with oysters in that scenario. Oysters are decreasing, eelgrass are increasing, etc. So the oysters NF and ENF stands for non-forcing. So we didn't do anything with the oysters or the eelgrass in this particular scenario. That's usually indicated by the gray line here. That's essentially our base scenario, what everything is going to be compared to. In some of these plots, that line might be black, but that's the gist of this key. They're grouped by color. The runs that are most influenced by eelgrass increases are in green. The runs that are most influenced by oyster population change, are coded in blue here, and those scenarios most influenced by eelgrass loss are in orange. So that's going to be true of the next several slides. They're going to look fairly similar, but this is one of those ecosystem metrics I talked about. This is total biomass in the system and how it changes across the scenarios over time. And one thing I want you to notice is there is a distinct separation in the results between these scenarios. So in that aspect, we believe our structure is informative of different changes taking place. Oyster change is relatively less than changes in the eelgrass scenarios, and there's some good reasons for that. And this system in Virginia, these two systems in Virginia, are already fairly rich in oysters. Not necessarily wild oysters, but we included in the model the biomass of aquacultured oysters. And then what is reflected in these scenarios is only the restored oysters. So that's the restored oysters in the context of all the other oysters in the system. It shouldn't be too surprising that we're not having a huge effect, but it is important that there is an effect here. There's more biomass in runs that include more restored oysters, and there's less biomass in the entire system without that restoration taking place. Eelgrass, in contrast, is already a constrained population with very few acres of eelgrass coverage. And so when we increase the eelgrass to a recently observed maximum, that in turn has a much greater effect. And when we further decrease what's already there, um, it has a lesser effect than the increase, but a greater effect than the oysters that are restored. Again, there's already a lot of oysters in these systems, but the restorations were important. This is a biomass of just predators. So a different output metric, similar results, but what we see is those scenarios are even more compressed. Um, and again, the y-axis is changing slightly. I should also mention that all of these figures that we're looking at that look similar here are from the York River only. And I'll show you later some combined results from both systems. But the York River and Piankatank River had very similar results. And just for simplicity, I'm only showing you the larger systems results. Trophic level of the system itself. So trophic level of the community is the output metric. It also changes with our different scenarios. And with more eelgrass, we get more predators, and the trophic level of the entire system increases somewhat. And likewise, we see the similar pattern over and over again in many different results. Trophic level of the catch. So now we're only looking at the species that we harvest, and not surprisingly, because those species are typically predators, the trophic level of the catch also increases over the scenario. Um, you've heard the term fishing down the food web. Um, that term refers to the same patterns we're seeing here with our decrease in foundational habitat of eelgrass. We get lower and lower trophic level of the catch. So more herbivores are being caught, less predators, less of those target species that we're usually typically very interested in, which are all commonly predators. So now we're transitioning here a little bit. We've been looking at ecosystem metrics and some examples and some similar patterns across different scenarios. But now we're going to focus on that particular species of interest, the most lucrative seafood in the Chesapeake Bay, the blue crab, and blue crab harvest specifically. And again, these results are still the York River only, but Piankatank results look quite similar. So we're going to look at first the oyster only scenarios. And with the oyster increase, we see a change of about 10% more relative catch. So one would be no change. 1.1 is a 10% change. 1.2 is a 20% increase in catch of blue crab. Um, Similarly, the decrease in 0.9 would suggest a 10% decrease in harvest. And in this case, the black line, now dash line, is our non-forcing scenario, smooth. So that focuses on blue crab, and similarly, this is the seagrass scenarios that focus on blue crab only. So again, this is only one foundational habitat changing, and in this case, what we're looking at is, an additional scenario you did not see in the other plots. In this case, this is the status of the population from the early 1900s. The population of eelgrass at the time was very dense and widespread. And what our eelgrass experts that we worked with told us after we did this scenario is that's not any longer a realistic scenario. Even so, I did want to share it with you to show you the difference in the system itself, and what we would have expected the catches to be in the early 1900s. There was a lot more eelgrass here, and it is a critical habitat for blue crab. To recruit to eelgrass, the little guys settle out in eelgrass and have protection from predators there. So the population was likely much, much larger. It's a bit irrelevant because we don't believe we can get there today. Instead, we simulated on those other figures and this figure the more realistic expectation that we could get to a recently observed maximum of eelgrass. And that's what our eelgrass experts suggested is the scenario we should stick with and focus on. And so that's what you saw in all the other figures. So this darker line is the expected relative catch of blue crab with less eelgrass than we have today. When we take this large scenario out and compare the magnitudes of the effects of both foundational habitats on expected catch of blue crab, and side by side, we do see that seagrass is having a bigger impact on expected catch of blue crab, but they're now on a similar scale. These are on par with one another, so you can actually compare improvements or um, or decreases for oyster and seagrass scenarios. So the final step for us, now that we've got a working model that is in both systems and we've got projected landings, we can make that connection to in-plan and produce different metrics. The in-plan metrics put our outputs in terms of jobs and dollars. And just a short anecdote of the importance of this. For more than 20 years, I've been working on ecosystem modeling and ecosystem models and outputs and trying to work with stakeholders. And it was really a night and day difference once we incorporated this translation to in-plan metrics of dollars and jobs. It's exactly the same models, exactly the same outputs, except that it's now translated into different metrics that people care about. In order to do this, we had to actually conduct some interviews of the industry, of the different fishermen that were out there, and the costs that they incur for their industry and their different harvest, blue crab and all the different harvesters that are out there for Virginia. But once we did that, we were able to quickly translate our results into um, into those metrics. And to simplify things even further, we're going to look at the in-plan results from only 3 of these scenarios. What happens without the restoration, what the economic impact for the region was for expected to be for a mature reef if we let this restoration develop and grow, and then a combined result if both of these foundational habitats are restored and grow and remain healthy. These are the results we're going to see in the next slide. So this is just a summary. We're going from our restored oyster reef, our current situation, um, either letting those animals grow or looking at either maybe there'd be a catastrophic loss of that restoration, or similarly, it's going to be the same result if we consider the condition of the ecosystem before the restoration took place. There's oysters there, but they're not in dense reefs, and it's a different ecology. And the third scenario is, again, allowing those oysters to grow like we have here, but also restoring seagrass at the same time. In this case, there's $300,000 less per year in the HFA. So now we're looking at combined results. Both models combined. This is the entire habitat focus area. So where the restorations took place in the Piangateg and the York together, there would be $300,000 less per year projected with in-plan. And this is the result of a 13% decrease in the harvest of blue crab only. So this doesn't account for all the other species that are harvested, but blue crab accounts for about 90% of the harvest values in this region. If we just look at the restored oyster and the value of that oyster restoration to the HFA, a habitat focus area, in the Middle Peninsula in Virginia, we expect a 25% increase in harvest compared to pre-restor. Well, actually, compared to our present day. So this is allowing it to grow 20 years in the future. We expect a 25% increase in harvest. And that, if we translate it through in-plan, results in $700,000 more a year in the habitat focus area region of the Middle Peninsula. Now, if we account for both foundational habitats being restored and growing and being healthy again, we're looking at a much greater increase in predicted harvest for blue crab. 122% increase in harvest. And when you translate that with in-plan, we end up with a $3.1 million per year gain in this relatively compact area. So with that, we should have plenty of time for questions. I'm going to wrap up with some thank yous. So thank you to NOAA Chesapeake Bay office for funding this project. Thank you for the watermen and the advisory panel that included those seagrass experts that advised us to limit our scenarios so we weren't looking at something that was unrealistic. And thanks to all of these folks that shared data with us. These efforts of ecosystem models are an incredible resource to integrate the information we have, but it really does take real data from a wide variety of folks that work in this area to make it work together. So with that, I just want to thank you for your attention, and we can address any questions that you might have.
Great. Thank you so much, Tom, for your presentation. Audience, as was said, we have plenty of time to answer your questions and we would love to hear them. And thank you all for being patient with us with our tech hiccups. Can you go back to the last slide?
Sure. So I'm assuming not the thank you slide, but um, although we're still thankful for all those people.
Perfect. Thank you. They got what they needed from it, I'm assuming.
Okay. Be more than happy to share this graphic with folks too, if it's helpful, or talk in depth about many of the other results that, aren't in this simple message, one pager. Uh,
Is it available online somewhere? Like, do you have a link or a website?
should be, but it's probably easiest just to email you. The organizers also have a copy of the PDF.
Oh, okay. Sounds good. Well, if anyone reaches out to us wanting that information, we'll pass them along.
Okay, thank you.
Yeah, no problem. Oh, we did just get a question, came in the regular audience chat. All right.
Yeah, and I just want to point out that this is my email if anybody wants to follow up with me afterwards.
I'm going to stop your screen share real quick because Vimeo only lets me do one thing at a time. All right. So you
Sure.
mentioned customizing metrics to stakeholders. In this case, the monetary value, but that there are also trade-offs. What would those be in this case?
So in the case of the three scenarios here, there are a lot of trade-offs. There's always trade-offs. There's never a silver bullet situation where one strategy is going to benefit everybody. Um, so in this case, with we were focused on summarizing the results for the most lucrative seafood species. We didn't look at a lot of negatives in that case. Um, it's a great question and one I didn't come prepared to answer. But there are always trade-offs, and we can go back and look at any metric you're interested in. Please just email me and we can continue the discussion. But there's a lot of information to sift through always with these approaches. And so if you're interested in a specific, group or species that we modeled, we can certainly look at that. The blue crab themselves have effects on the environment, on the ecosystem. Um, so more blue crab mean more of those effects on the system. All of their prey is being depleted when there's more blue crab. Um, so if you're interested in any of those species, those are the kind of trade-offs that result. If there's more foundational habitat, though, um, the downsides are going to be minimized. The trade-offs are minimized. So, for instance, um, the striped bass population, usually people are interested in that as well. This oyster restoration didn't have a huge impact on striped bass, although striped bass will feed on the prey that come there. It's largely a pelagic species. So both of these restorations would be enhancing the benthic species, um, and that changes the balance between the benthic and pelagic coupling. Um, and although striped bass will benefit from the prey being produced, they're not going to have a direct benefit. Um, so it's not a direct trade-off. Um, I just don't have a good answer for you unless I have more details to your specific concerns, or if you're just talking about trade-offs in general. Yes, there are always trade-offs. Um, I if you want to recharacterize your question to follow up, I'd be more than happy to pursue that. I do see another question. Have you given much thought of incorporating things like market value of carbon credits of oyster filtration functions? And we haven't pursued that. It was beyond the scope of this project. The topic had come up, but it wasn't a metric that we could readily produce. And there's a lot of uncertainty with the market of carbon credits. So we didn't pursue that further. Okay, thank you. All right, I see your response.
Awesome. Thank you so much for your response to both of those questions. Someone did, not necessarily a question, but if time permitted, and we do have a little bit of time left, they said they would like to hear about the other economic benefits to the three scenarios on the last substantive slide.
So, um, I mean, you can talk about jobs a little bit. Keep in mind this is a relatively limited region, but definitely jobs are always of interest to folks, our stakeholders especially, and the natural resource managers. In the situation where um, both oysters and eelgrass are restored, so the best scenario for habitat, um, we're talking about an additional 30 jobs in this region. When oysters are restored and ignoring eelgrass, so eelgrass is there, but we didn't do any forcing of that population, there was still an additional 7 jobs in the region, just from the oyster restoration alone. Um, if we, before the restoration took place, so this is less oysters, non-restored oysters before the restoration took place, our in-plan results suggest there were 3 less jobs in the region. In the worst case scenario, so we lose our restored oysters, we lose more eelgrass, we expect a loss of 12 jobs to the region. So if that's if there's anything specific I could maybe give you more information, please just follow up with the chat there.
Awesome. Thank you so much. And then there was a follow-up. I think it's a follow-up to the previous question about the market value of carbon credits. Let me put that on screen. Thinking about the ecosystem benefits as quantified in the mass balance models, but represented in terms of additional kinds of currencies, carbon credits, biodiversity credits, water quality credits, and things like wetland banks.
So I'd love to think about this more, but it doesn't translate from implan. Implan is really all of its focus is on the one industry of harvested fish or populations. So our fisheries, in that industry is the focus. So um, it there's no direct translation to other metrics. It's really the jobs and dollars, and I mean there are other in-plan metrics, but it's all about the commercial fishery itself. So it would be possible to look at that with more information um, about the carbon credits and what specific aspect we take out of the models to estimate those carbon market values. Um, is it sequestered carbon in seagrass? We also have marsh in the models. Is it the carbon that's sequestered in the oyster shell? We can look at specific aspects based on our outputs, but we're going to need to translate it. So use another modeling approach, something like Implan does for jobs and dollars, to get to those carbon market values, if that makes sense.
Great. Thank you for your response. And they included their email address, which I will pass on to you after the
Great.
presentation as they want to follow up on this further.
Yeah, I'd love to talk about this further and what possibilities there might be to use our results in other ways. Appreciate that.
All right. And I believe that was all the questions we have in the queue. I don't see anything else there or in the chat. So I think we can go ahead and wrap up today's presentation. Thank you so much for sharing your work with us today, Tom, and thank you, Corinne, for organizing today's event. Do you have any final remarks, Corinne, for us?
I do. I would just like to remind the audience that the seminar series will be taking their annual summer vacation in August. So we look forward to hosting the next series on Wednesday, September 10th. And I also want to extend a huge thank you to Tom for a beautifully laid out study and wildly successful Q&A, as well as a thank you to you, Cassandra, and the NOAA Library. Your poise and professionalism are unmatched. So thank you very much.
Thank you
Thank,
all.
thank you. And thank you, audience, for joining us today. We hope to all see you, as Corinne said, in September. Thanks for attending and have a great rest of the day.